Welcome everyone to day one of Qiskit Fall Fest at the Catholic University of America. We are super excited to get into it. Um, for all of you who just joined because you saw my awesome flyer, Qiskit Fall Fest is a global celebration of quantum computing supported by IBM Quantum. This year, there's over 150 universities participating all around the globe throughout the months of October and November, and we are one of them. And the purpose of the event is to learn and get excited about quantum computing and use Qiskit, which is IBM's open source quantum computing resource. I am Natalie Lee, and this is my first year at grad school at Catholic University, and I'm interested in pursuing quantum computing research. It's been an interesting first year, and this event has been a big part of it. I'm co-organizing this event with my advisor, Dr. Daniel Sierra Sosa. So thank you for inviting me to help with this. And before we kick off our speakers, I just want to say a special thanks to IBM Quantum for allowing us to host one of these events at our university. And a special thanks to the Physics, Engineering, and Computer Science Department at Catholic University of America for supporting our endeavors of quantum computing research. And I would like to give a shout out to my lab, the Rift Research in Future Technologies Lab, that has been helping me set up this event, helping me pick colors for my flyer and carry water bottles up 3 flights of stairs. I really appreciate it. So thanks all of you all, and thank you to the audience for attending. I don't know how many people we have joined right now, but uh, it's all thanks to you all that we can host these events. Okay, and we have an exciting lineup of speakers that will be seeing the next two days. And the schedule for today, I'll be handing this over to Nick Braun, who will give us a lecture about an introduction to IBM Quantum and Qiskit, and he'll get us started. So Nick Braun, he's a global strategic research development lead at IBM Quantum, and he was given, or he luckily said that he could present at our event and start us off with a very perfect introductory lecture to get this 3 days of quantum computing learning started. Okay, so I'm going to hand this off to Nick, and I'll let you share your screen. Um,
All right, I'm sending you a request.
okay, great.
And I am sharing. Can you see my slides? It looks like your slides, but it has my name on it.
Yeah, I can see your slides.
Okay. All right. Well, I guess let's get started. I'm happy to be here to kick off the first day of the Catholic University of America Fall Fest. And I've been working in IBM and quantum for 12 years. I've worked on the hardware side, as you saw from my bio. I worked on now on the software side and algorithms and kind of moved to the business side of things. So I worked on a lot of sides, and I'd be happy to take questions. At the end of this, we have like 15 minutes or so reserved for questions about anything you like, even if I'm not talking about it in this talk, because there is a lot of stuff going on in quantum, more than you can fit in 45 minutes. So I'm going to start this from the beginning, and just so like everyone gets on the same page, we're going to talk about what is quantum computing. And in order to do that, basically, we need to introduce three concepts from quantum mechanics that are what going to be allow us to power the ability for quantum computers to be able to do amazing things. These concepts, which I'll go into, in greater detail, are superposition, the idea that you can be in two different states at the same time. Entanglement, where you have incredibly strong correlations between two different qubits or quantum bits. And interference, which is a kind of tool used in order to boost the probability of measuring the correct outcome. Interference, like the way waves interfere with each other. So we'll go into that. And as you know, IBM being in quantum computing, one of the reasons we are always looking to the future of computing is because we know Moore's law, which is this law that says the number of transistors will double roughly every 2 years. We're approaching the limits of that computational power. And in fact, classical computation has fundamental limits because certain kinds of problems do not scale very well. Even if we were to shrink down the transistors even more, we've gotten them down to 2 nanometers currently, which is about 10 silicon atoms wide, which is really, really small. In fact, quantum computers offer such power that if you're at the level of about 100 qubits, I'll keep calling them qubits, you are not able to simulate the ability of a 100 qubit quantum computer to perform calculations. Not exactly. There's always techniques you can try doing for certain kinds of problems, but if it's sufficiently complex, quantum computers offer the ability to do things that classical computers cannot even think about approaching, like ever. Um, okay. All right. So basically one way to think about this, and I'll keep coming back to this, is how do we deal with classical computation in the first place? Well, everything that we know from this Zoom call um, to all the calculations or word processing or internet things are done because we can encode information into zeros and ones, and that is the language of computation as we know it. That's fundamentally the unit which we're doing classical computing, and has a many 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 decades of history, and it's brought us the internet, it's brought us AI, it's brought all kinds of great things. But there's certain things that we might be able to do to go beyond that, and that's where quantum computing comes in. So instead of just ones and zeros, well, let me take a step back. I'm going to continue with the classical computing and saying that um, in order to think about how do we actually execute classical computations, well, we encode everything in zeros and ones. And so your bit is going to be this classical thing that can be manipulated by a series of transistors, which form these logical circuits called AND or exclusive OR. But all these things do are classically they perform a Boolean logic on the classical bits themselves. And that means that, say, if I have an AND gate, like 0 and 1 is going to be 0, because both of them need to be 1 to both A and B need to be 1 for the AND to give them 1. So 1 and 1 is 0, but 1 and 0 is 0. Likewise, the OR and the exclusive OR, meaning both of them can't be 1. For example, but we're not going to go into that. We all took circuits class way back in the day. We're going to move to what the quantum part looks like. And the quantum bit, you actually have the ability to do superposition. So we can represent the state as something existing on the surface of the sphere, where we have labeled 0 at the North Pole and 1 at the South Pole. And that's kind of done for historical reasons. And then the way we operate on these quantum bits is through this thing called a circuit. And the circuit is as the circuit is drawn like this, where we have the bits of information, just like we had in the classical circuit. And as we move from left to right, we're going to perform operations on the qubits or between the qubits, and then perform measurements in the end. So in that way, it's kind of written like a musical score. I think that's a pretty good analogy for how we think about it, but it was originally made to be an analogy with classical circuits. And we'll go into what these do. So when you are a qubit, you have different states, and these kind of correspond to probabilities, but they're a little bit more general than probabilities. They're actually given by probability amplitudes. And so we say the state A and the state B are weighted by the probability amplitudes of A and B. Now, that means you can see that you can encode two pieces of information, for example, into the qubit. And then the description of quantum mechanics is that, well, I need to put, classical data into my quantum computer or into my qubit. But when I measure it, because we don't observe, day-to-day kind of quantum mechanical effects in our lives, which kind of makes it strange, what happens is when we measure quantum systems, we can only get classical information out of them. So when we perform a measurement on the qubit, we will only get 0 or 1 out, and the probability with measuring those is going to be the square, or technically the absolute value squared of those coefficients. So these probability amplitudes, which are the coefficients of the 0 and the 1, translate into probabilities that you actually measure classically, these A and B squared. So that is where the kind of stochastic or probabilistic nature of quantum mechanics comes in. Okay, so for example, we can do certain gate operations such as an X gate. What an X gate does is it takes a zero to a zero state or wave function and flips it to one. And so if I initially started with the state zero and I measured that, my probability would be 100% of measuring zero. So I can measure the exact outcome. And if I flip it, then I will get with certainty a one out when I perform a measurement. So that's kind of how the probabilistic things work. What's more interesting is when we have a combination of zero and one, which we call a superposition. If we use this thing called a Hadamard gate, which is represented by the capital H, that what that does is it takes a ket zero to a superposition of ket zero and one, where those zeros and ones are normalized by this one over the square root of two. That's done in order to make sure that the probability of measurement corresponds to 100% for each case. So if we're able to do that, then we can then perform measurements, but we will find that we will get the zero result half of the time and the one result half of the time, corresponding to the squares of these one over root twos, one half. So that's interesting. So we've actually, I mean, it's interesting because you take something definite, like I know this is the state 0 plus 1 divided by square root of 2. But when I perform a measurement, I get a random outcome, and that's just the nature of quantum mechanics. But it's something we have to keep in the back of our head. So the superposition, what is happening mathematically is these zeros and ones are technically living in something called a complex space, the complex plane. And these are just kind of placeholders for these column vectors 1, 0, and 0, 1. And us physicists, we like to use these because we're lazy and they allow us to perform calculations a little bit easier instead of writing down the whole matrices. But at the fundamental end of the day, this is just a matrix math. And so your superposition here is just going to be the, basically it's just the column vector AB is the same as this A ket 0 plus B ket 1. And then these A's and B's have the probability that we normalize them. We can always normalize that later. That gives us the probabilistic interpretation of measurement corresponding to those states. And then we say that the quantum states are equivalent if they only differ by a phase. We usually say global phase because a global phase is not observable, which means if I take the absolute value of it, I measure the probability, there's no way for me to get that phase outcome. So that is just some math right there. And then we represent these things on this thing called the block, these states on these things called the block sphere, which you can kind of think about as like Earth, where zero is the North Pole, one is at the South Pole. And then any point on the equator is going to be a complex superposition of zero and one. And that's what people mean when they say zero and one at the same time. It's actually a linear superposition. So measurement is forcing the state to collapse into the zero or one states, and it will do that with these probabilities A or B. But interestingly, you can change these coefficients and you can, tune the probability of measuring zero or one by moving the state to some, say, arbitrary location, the block sphere, like it is here, kind of in the northern hemisphere. Okay, then entanglement is the other trick. Entanglement has to do with the fact that when we have more than one qubit, we have two qubits, right? They are able to represent a combination of four states instead of two. And so you have an A, B, C, and D here with the same kind of normalization condition. But if you if you are able to do that, then you can get these correlations between the qubits where they are entangled and you cannot describe the qubits independently of each other. They can only be described by this collective wave function, which means you can't describe them separately. And to kind of see how that works, we can write down these states like just simple examples of these states of two qubits. And to the lower left here, I should say that the qubits that are next to each other, like with an edge between them, are ones that we can natively couple with, say, microwave pulses or certain kinds of controls that we actually do in the lab. Mathematically, we can write all combinations of zeros and ones, and we can see that the first one, I'll show you in a sec, is not entangled, whereas these second two are entangled qubits. And one way to see that, basically, when you look at this mathematically, the way you want to see it is that you can factor, if you can factor the qubits into one description of one and one description of the other. In this case, I described the first qubit with a zero state and the second qubit with a 0 plus 1 over root 2 state. Then I can describe those separately and they are not entangled. But if you can't factor that, so you have this 0, 0, and 1, 1 here, there's no way for me to write that as a product of the description of the first qubit and the second qubit. So they're entangled in that you can't factor them out, basically. And that kind of gives you an idea. So when you write down number of qubits, you can have 8 possible states, and you get this exponentially large ability to represent states with qubits, which is where the computational power comes from. And then how do you manipulate these things? So I think this is what you'll get to the point of doing this with Qiskit later, is we perform operations. We call them gates typically. These are very similar to the logic gates in classical computing, like the and exclusive or. Instead, we have different kinds of operations we can perform. So we talked about the Hadamard gate, for example, that will take the ket 0 qubit to a 0 plus 1 normalized by root 2. We can perform measurements on these qubits, and that will give us a probabilistic outcome. We can perform other kinds of entangling operations. There's numbers of ways of doing this. This one's called a controlled knot here, which will flip the state of qubit 1 conditional on the state of qubit 0 being in the 1 state. So it basically is an X acting on qubit 1, but the X only acts if qubit 0 is a 1, which is what the control does. It's a controlled flip. And then we can build, bigger and bigger kinds of circuits out of these. So this is kind of a encoding and decoding type problem where you might use this as a primitive for something called quantum error correction, which I'm not really going to talk about today unless you ask about it. I'll be happy to. So you can put these many, many qubits together, and we can draw these things, but we developed a programming language so that we didn't have to like actually draw these by hand and then turn them into a computation with microwave pulses on our circuits. Okay. And then the last concept, the interference, kind of comes into play in that a lot of the way algorithms work is they need to destructively interfere the incorrect solutions and constructively interfere the correct solutions in order that you maximize the probability of measuring the correct one at the end of the day. So you want to increase that amplitude, make it, push it towards one. And there's a number of tricks for doing this. For example, one of these is often used in something called Grover's algorithm, which I'm sure you'll probably learn about later today. And it involves marking the correct solution, the 0, 1, 0 in this case, around the access, and then flipping the states of all the qubits such that you amplify the probability of measuring the correct one. And if you do that, in the correct way, you can, always get a better than 50% chance of measuring the correct one. And if you, measure enough times, there's a guarantee that you will get the correct answer to within some certainty. And so this interference is very important in a lot of the algorithms, such as, doing things such as that require the quantum Fourier transform, for example. That kind of interference provides answers for some very important algorithms for things such as phase estimation and Shor's algorithm for factoring. Okay, so as we're going along here, I'm going to go talk about how do we actually implement this with Qiskit and what do we do with it now that we have this basic idea. So Qiskit is the open source software development kit pioneered by IBM. I've worked on it quite a bit. I work only in it pretty much. And it is actually just kind of like one part of a large catalog of things that go on under the hood. Namely, in order to interact and do useful computations, for example. So the Qiskit software development kit is this open source part. We have it sitting on top of ways that it can interact with basically the cloud or basically with other kinds of classical computers. This high performance computing integration, which is a relatively new thing that we've put out with it. It's also open source. But mainly you want to get down here to the quantum computer. And in this compute area, we have something called Qiskit Runtime, which takes care of handling these circuits that you submit over the cloud. And they will run them, convert the instructions into microwave pulses, and they will actually interact with the qubits, which live in your quantum processing unit on a quantum chip. And that is the quantum part of computation, but there's a lot of other parts of computation, such as using CPUs, like you have in your laptop, perhaps. That's a uh, central processing unit, and QPUs would be the quantum processing unit. We also have GPUs, which are graphics processing units, which are very good at representing these things called tensors, which are representations of matrices that we can do very fast parallel type computing on. And then, so next to the Qiskit software development kit, we also have things called add-ons. The add-ons are also an open source thing where we have built some techniques, for example, like techniques our researchers come up with that are going to be useful for other people, such as your research professors at universities, to implement techniques that they say IBM pioneered to help them do to help them use the best techniques for getting the correct answers in whatever kind of line of work they're doing. The other thing I'll talk about a little bit is the Qiskit transpiler service. Transpilation is basically the process of taking a circuit from an abstract circuit to a circuit that is executable on hardware, a more native, or you might call it like machine code, kind of like something that takes Python and converts it to machine code. That's a compiler. I guess the transpiler is because you're taking a circuit to a circuit. And then the functions catalog is kind of like you might think of it as an ecosystem, a network of startups that we have that are building basically services like kind of like apps on top of the ability to execute them on IBM's quantum hardware. And so in that way, we can get the people who know how to solve useful problems writing software that will use our quantum computers to and even classical computers to interact with them and provide useful solutions for people that don't necessarily need to understand the low level of quantum details that I'm talking about today. Okay, so just to talk about like what do you get out of a quantum computer? This is kind of an idea of how when I write an algorithm, there's usually like three steps that I'm thinking about it. First of all, we usually just assume that the quantum computer starts in the state with all zeros. So everything is initialized to zero, and we need to prepare whatever our starting point is from that set of zeros. And so we usually call that state preparation. And then the quantum algorithm more or less acts on that state that we want to look at. So a lot of times that could be I want to prepare a wave function of some molecule. My quantum algorithm is going to evolve that with time, for example, and then we'll do some measurements at the end. And what I'll talk about is the different kinds of measurements we can do. So if I was to execute this algorithm I showed you right here, and I was to do it one time, I could get some sample output. And one of those outputs might be measuring the first qubit in a one, the second qubit in a zero, the next three qubits in a one, and the last qubit in a zero. And that is called that is one experiment. We usually call it one shot. It is one data point that we get out because I can only get classical information out of my quantum computer. But a lot of times, what I'm not exactly interested in this because I know I will get this with a certain probability if I just happen to get it that time. So what you often want to do is you want to get a probability distribution out. So you want to repeat this experiment thousands of times. It's pretty common, even tens of thousands of times. These run very fast on our hardware, so it's very easy to execute a lot of these shots. So you can get out a probability distribution of all the bit strings that you can possibly measure, and then you have the frequency of how many times you actually measured it, and so you can calculate the probability. Sometimes we just sum up the counts as it's done here. And with that probability distribution, it tells us something about the nature of, say, the wave function we're trying to analyze. So the samples is one way of getting a result out, and that's getting the results out in terms of zeros and ones. That's the main thing to remember. There's another thing called observables, which we use something called the estimator for. And observables correspond to things that we can physically measure. So, like, for example, popular observables might be the energy of a molecule. And that is something that we can write down wave functions of molecules for, and we can translate them into measurements to be performed on the qubits. And those measurements lie on different axes. So I talked about the Bloch sphere. Um, and the Bloch sphere, the z direction, the up and down one going through the north and south pole, is the standard way that qubits are measured. And the zero value corresponds to a z measurement of +1, and the one state at the south pole corresponds to a z measurement of -1. So each of these x, z, and y's, they can be anywhere between 0 and 1, but we have to measure each one a number of times so we can average it out to get the measurement along there. So basically, like the z-axis is the qubit measuring this way, and the x-axis I'll show on another slide is kind of the direction along the equator, and then the y would be the same direction along the equator, but 90 degrees out of phase. And from a quantum mechanical description of a molecule, for example, we can construct these observables from which we can execute on a quantum computer. And a lot of those, yeah, a lot of these could be, as an example, you might want to find the energy and you want to try and minimize that energy. That's a common technique that we use, or for say cost function. Other observables, for example, could be magnetization, polarization, like kind of anything you can physically measure is considered to be an observable in quantum mechanics, and this is how you write them down quantum mechanics. So they're amenable for quantum computation. To just give you a flavor of an idea, I'm not going to go too into algorithms today, but there's a class of algorithms that are hybrid between quantum and classical, and one of these is called a type of algorithm called variational quantum algorithms. And this is to kind of highlight why this observable might be used. What we're going to do is we're going to have a quantum computer and a classical computer, and the output of the quantum computer is going to go into the processing of the classical computer and then get fed back. So what we're actually doing in a lot of these is we do the execution of some sort of quantum algorithm. You'll often see this block of code or as an algorithm as this U. The U stands for a unitary matrix because all of these gate operations have the property that they are unitary, which means for one they are reversible. And a lot of times they are parameterized by some set of parameters we just usually call, say, theta, for example, in this case. And what we'll do is we'll perform a measurement as a result of that state. In fact, we'll perform a number of measurements so that we can average over all the discrete values. And then what I should actually say about the quantum circuit is in variational quantum algorithms, a lot of times this is given by something called an ansatz, which is kind of like a guess for the structure of your problem. And this ansatz is going to be some combination of rotations around the block sphere of each qubit. And that can be done by differing angles, which is why this theta is parameterized here. And then we have some set of C naughts here. So we're entangling all these qubits together, and that entanglement is based on this parameterization. Now, once we execute that, we measure that and we measure in the different bases so that we can then get a result such as an energy out, and we put it through a optimizer. Often we are using these optimizers to find the minimum energy, which is something called the variational principle of quantum mechanics says that no wave function can have a higher energy than the ground, or yeah, no wave function can have a lower energy than the ground state. Therefore, the lowest energy that you can find is going to be the best kind of job you can do. So a lot of these variational, especially the variational quantum eigensolver is reliant on this variational principle, in fact. But we might also use a cost function such as you use in machine learning, where you try to minimize, say, a cost function. And there are many quantum algorithms that behave like that. So you can think of this as perhaps a training on the quantum computer, and minimizing the cost function is the feedback that the classical computer gives to the quantum computer to attempt to minimize that cost function. Um, so one of the things you have to do before you do that, I mean, you can go deeper and deeper into these things. You have to convert this into what's called an instruction set architecture quantum circuit. So this is where you use the transpiler to mainly do two things, two important things, which is if I showed you the picture of the quantum computer, uh, you'll see that not all of the qubits are connected to each other. The connections are actually defined, by the metal. They're like physically made in these qubits, like much like transistors are. So you can only natively entangle the qubits that are next to each other. But what you can do is you can always insert these things called swap gates to move the quantum information around the lattice. And so one of the first things the transpiler will do is insert these swap gates so that it can be the quantum circuit can be mapped to the native graph of that device. The other thing is there's only a specific limited instruction set that we're using. So that would be like we like to use square root of X rotations. We can do arbitrary Z rotations. C naughts used to be our native entangling gate. Now that's C phases or CZs. So basically, you have to translate this, what could be a relatively simply looking circuit, and it will get mapped into something that's a bit more complex. But we will respect those rules in that there's a limited set. So these little barbell looking things, these are the CZs. The square root of X's are implemented with microwave pulses. The Z rotations are implemented in software. It basically changes the angle of the phases of the subsequent pulses. And when we want to do these measurements, for example, for measuring an observable, then we're measuring these X, Y's, and Z's. What we actually do is natively we can't actually measure in those directions given the hardware. We can only measure in the Z direction given our superconducting qubits. So what we do is at the end is we rotate the basis. So we rotate that X axis into the axis of the Z so that when we measure, we can correspond to 0 and 1. And from those zeros and ones, we can calculate what the resulting observable of X would have been. And of course, these are probabilistic, so you get a whole set of these things, and often you'll average them together. And then you might need to multiply it by the values of other qubits to get those longer strings. Um, yeah, so you can also do smarter things. So because of Heisenberg's uncertainty principle, you cannot measure X, Y, and Z at the same time. So when you perform this rotation and you collapse the quantum information, you collapse it along the Z axis, which means that when you rotate back and try to measure, say, the Y value, for example, then it's not going to be compatible with the measurement that you've already done. Um, so what that kind of means is the order that you make these measurements in matters. So you can't simultaneously know, say, both X and Y at the same time. But there are a set of observables, such as ones that act on different qubits, that can be done at the same time. And we call these commuting observables. So this due to the Heisenberg uncertainty principle, we can only measure, say, we can't measure this entire observable at the same time, but what we can do is we can group it into terms for efficient measurement. So for this case, it would consist of two groups, and that's going to be at least more efficient than just measuring the five terms by themselves. So these are kinds of tricks we use to get the observables out from the most efficient number of measurements. But you can also, these shots and these shots and these observables do correspond to each other in a certain mapping, but that's how they're related. For the shots, we measure everything at once, and so that's just gives us these zeros and ones, for example. Okay, so there's a number of things that kind of go into building algorithms. This one's for a particular class of algorithms called variational algorithms, such as this ansatz, which is the circuit structure, how you transpile, how do you implement your observable, how many shots do you need to measure to get within the correct accuracy you need of your observable, such as your energy. So that's very important. And we kind of have like mapped this idea of how to run a quantum circuit into something we call a Qiskit pattern. Um, and so a lot of this is, we've basically broken up into four results. You want to map whatever problem that you have at hand into something that can be represented with quantum circuits and operators. These are things that the quantum computer inherently knows how to operate with. So kind of the native language, you want to encode your problem into something that makes sense for the quantum computer to operate on. And then we want to look and optimize that circuit for the actual hardware that the quantum circuit's going to run on. We're going to actually then execute this via Qiskit runtime. So this involves taking all those gates, turning them into microwave pulses, doing the measurements also with microwave pulses, getting the results out. A lot of processing, a lot of physicsy processing I used to work on is involved in that. And you get the results out whether zero ones or a set of zeros and ones, like a probability distribution, or observables for your results. And then there's a number of things we can do on top of that. So what the Qiskit circuit library basically does is it allows you to build these circuits. And so you'll get experience doing that this week at this Fall Fest. And a lot of these things have to do with inputs from areas or domains, as we call them, of expertise, such as chemistry, material science, optimization, computer science, quantum machine learning. Um, there's well-known ways that people can encode those kinds of problems into quantum computers. We get circuits at the end of the day, and we need to convert those circuits into some kind of circuit that will run on the quantum computer. We need to execute these and get the expectation values or samples out of the system. And then we need to process this in some way by showing the results or by averaging things, or there's a number of ways of processing the data to get what you want back out. And these Qiskit add-ons I mentioned before are techniques that kind of sit on top of here, whereas what I had just said on the previous slide was kind of the basic implementation within Qiskit. We have built a lot of things on top of Qiskit. So these add-ons, for example, sit on top of each one of the patterns and they do something different. So for example, this approximate quantum compiling tensor here is a trick where you can take a circuit that usually is used to represent simulating something like a material or a molecule, and the AQC tensor will give you um, an approximate circuit using tensor network methods that will perhaps run more efficiently on the quantum computer that you have. Multi-product formulas, there's similar kinds of tricks of breaking your problem apart into smaller problems that run better. Operator propagation is another technique where you can put in more efficient, more shorter circuits. But you you will have a lot more circuits you have to put in to make up for that shortness to get the same answer. And operator backpropagation is a technique for kind of getting rid of the circuits that you don't really need to run. You can kind of trim them off because the amount of error that will contribute is less than what you would get from executing them natively. Yeah, and so then the primitives are the Qiskit runtime. Other techniques, one I'll kind of mention is called sample-based quantum diagonalization. This uses the output of a quantum computer to be the output of the quantum computer is the input for a supercomputer, and the quantum computer is kind of the first step of the algorithm, and the supercomputer uses the output of that to do a different kind of hybrid computing. So one of the things we use quantum computers for is to simulate nature. I think I've mentioned chemistry and materials along. I'm a condensed matter physicist by training, so materials is something that I studied a lot when I was in grad school. And one of the things about that is it's very hard to simulate these kinds of things because electrons or materials or nuclei, they all have this property that the more you add, the larger the exponentially large space that you need to simulate them, which is why quantum computers are going to be very good for simulating physical things such as materials and molecules. There's other kinds of things with structures that we can even map onto different areas. So a lot of optimization problems can also be written in a similar way to that language of materials um, and molecules. So we know at least one well-known way of solving optimization problems, but we actually are pretty sure there's a lot more because we think that kind of any problem with a structure we can exploit, and that's kind of why quantum machine learning is also a very hopeful area for quantum computers. So, when you are trying to get the solution to something, you have to choose what kind of computer you want to use, but really the answer is usually going to use a little bit of both. So classical computers are really good at doing certain kinds of problems, but say there's these problems involving electrons or nuclei or whatever that will never be solved by a classical computer because the classical computer can't represent that exponentially large space of possibilities. Quantum computers are expected to be able to solve those, but there's a lot of things you wouldn't want to use a quantum computer for. It's good for these types of problems. Just like the reason you would use like GPUs for AI, it's a good type of processor for that problem. Um, Now we have a number of algorithms in quantum computing, and we know how to do this. But a lot of these are not what we call timely because a lot of what we're doing is we're trying to scale these systems in terms of number of qubits, but there's also a lot of physical errors that occur on these qubits currently, and our stage of existence, right now, our error rate for entangling gates is like about 3 in 1,000 operations. So that's like 0.3%. And our error rate for single qubit operations is like 10 times less than that, maybe one or two in 10,000. So if you have a long circuit that involves a lot of operations, the more operations you do, the more error you incur. And so we're limited by how many operations we can actually execute on the quantum computer, which prevents us from doing a lot of the algorithms that we know have this exponential speed up. So what we kind of mean when we think about these is those are solvable problems with a quantum computer. We just don't have the right quantum computer yet. We have a roadmap. We are going to build it. We have ways of reducing the errors. That is a whole field of study called quantum error correction. So we're kind of thinking about like what are the things that we can do now with what we have, and IBM is quite confident that we're going to be able to do something interesting with this still relatively noisy hardware. If we get it, just unnoisy enough, we can still do very cool things because we know we can build systems that are outside the realm of classical simulation. So trying to figure out these interesting problems and timely problems is a lot of what is being done. And like I said, there's a lot of techniques that will say for you don't really need a quantum computer, for example, for like playing video games or for doing the Zoom feed or whatever. That is actually quite well handled by classical computers. The clock rate of classical computers is much, much faster than any quantum computer will be. And there's nothing, inherently needed for quantum in that area. On the other side, we know where there are very hard problems, but they require such a large number of quantum operations that they'll incur too much error so that when if we were to attempt to execute them now, we would just get noise. Those are like Shor's algorithm for factoring, Grover's algorithm for any kind of large system. So a lot of that is we're thinking about we're always thinking about errors. So the sweet spot happens to be where we think we can do something that doesn't require as many operations so that the level of error we get is minimal, yet we're trying to figure out something that's interesting that we can solve with a quantum computer. And that's, kind of along these lines of optimization, chemistry, and materials is where we think that will be. And that's kind of how we break down these algorithms. There's kind of a well-known set of algorithms used on quantum computers that will address these different areas. So we usually put chemistry and materials together. Those things are inherently quantum mechanical. They're going to have wave functions associated with them. We know how to map wave functions to quantum computers very well. Optimization, we know we can do some similar types of things. Machine learning and AI, we have some theoretical evidence that it can be good, and sometimes people just do it and get better answers than they got without using quantum, and so they're happy about that. That happens to be how a lot of machine learning researchers work. Numerical simulation, say, solving differential equations for like fluid dynamics or plasma physics, that's something that relatively new in the field of quantum computing, but has been shown to have gotten a lot of people exciting because solving differential equations is relevant to all kinds of different areas of engineering, not to mention physics and the like. And then these apply to these kinds of domains of expertise where you have, built companies that are concerned themselves with building planes or cars, for example. So this is kind of how we think about, from the business kind of value on the right to like what class of domain these belong into, what kind of algorithm would they be addressable with a quantum computer, and then what does it take to actually make that happen. And then yeah, some of those are going to be nearer term, like the ones that look more like a native quantum system versus the longer term ones. Um, so we know that there are what we expect is that quantum won't be able to solve all kinds of hard problems, which are often called NP problems in computer science. I'm not a complexity guy, so I will let Natalie take care of that for me. But there's a lot of problems that we are quite sure are very hard for classical computers that are actually pretty easy for quantum computers. And that generally means the scaling of the problem doesn't blow up as the problem size gets larger, or it would blow up for a classical computer, but not for a quantum computer. And just to give you an example of one of the recent results that we had, it looks like this. So this is a um, type of chemistry problem. It's looking at a certain molecule, a certain catalyst that consists of four iron atoms and four sulfur atoms. And if you want to try and represent the wave function of this molecule, you can do that using a certain basis set, which is kind of the atomic type orbitals that you would use to put these things together. What you can do is use a set of qubits, and I think for this one, yeah, it was 77 qubits. We map um, the idea is basically we are going to map all of the orbitals of this molecule onto the quantum computer, and we're going to say that qubit is a zero if there is no electron in that orbital, and that qubit is a one if there is an electron in that orbital. So what that means is when we perform the algorithm, we would, in this case, measure a probability distribution, and the probability distributions will be strings of zeros and ones, and each one of those zeros actually means I have an electron, or zeros means I don't have an electron in the given orbital corresponding to that qubit, or I do have an electron if there's a one, and I take that data, and that data represents information about the wave function of the molecule. I take that data and then I can process it using a supercomputer, or you can even do it with your laptop for a small enough problem. And we have all this online and open source, so you can do this. And then we can look about like how good of a solution can we get using this technique. So we're gonna use the quantum computer to figure out something about the probability distribution corresponding to the wave function of the system, and then process that wave function on a supercomputer to get some answer, such as the ground state energy. It's a very common thing to ask about. And we were able to compete with some of the best approximate classical methods. So this problem is out of the ability of any supercomputer to do exactly, but we have approximate methods such as density matrix renormalization group theory, which allows you to use tensor networks to do a pretty good approximation. But even then, that kind of takes 8 hours for that tensor network to do it. You can't represent it classically because it would take 63 petabytes of memory. That's bigger than anything we have uh, out there, I think. Yeah, it's written down there. And then the quantum method is actually very good because the quantum method can natively process these kinds of information very well. And then we take that information, move it onto the onto the classical computer, and it takes an hour and a half. So we can start comparing like costs of what is the more if like cost-effective way of simulating molecules by doing this. And that's kind of where we're getting. What is the cost of this, and what is the accuracy compared to the best other answer we can get? And that's kind of where the field is going to progress in the next year or so. You're going to start finding examples which we call quantum advantage, where you expect the quantum answer to be more energy efficient, cheaper, more accurate, for example. And then these kind of applies to all of these like fundamental domain problems, such as longer lasting car batteries, so that you don't have to charge, you don't have to pull off the side of the road and charge as much. You want to have stronger alloys for planes because that will take less fuel and so less cost, less pollution. Um, a lot of things, drug discovery are reliant on these chemical processes, so we're doing things there. There's things that I love, like superconductors that are materials, things that need to be optimized for their usage, such as magnetic resonance imaging you get in a hospital. So that, I mean, there's a lot of classes of problems like that. That's just to give you a flavor. But in my last minute or so, I just want to say the next steps, we have some learning that we have on we adamantly believe we need to teach people about quantum computing so that they use our computers to discover the next algorithms that are going to make breakthroughs of relevant business value. So we put a lot of stuff online to teach people how to do that. So we have this IBM Quantum Learning. There's a whole community of that learning. There's this thing called the Qiskit Advocates Program, which that just opened up that allows you to kind of throw events like this Fall Fest. We have other things such as the Global Summer School, which runs virtually every 2 weeks, the Qiskit YouTube channel. You might even find videos of me on there. And we have, for example, developer certification. For students like you, the Qiskit Advocate Program is something I would very much recommend, especially because this can come with more mentorship opportunities for like doing projects with Qiskit, getting to know people in the community, and getting access to events and all kinds of fun stuff, making contributions to open source code. I've had the pleasure of mentoring some advocates myself, and we had some pretty good projects. Paul, in conclusion, I know well, I can go a little later if we have more than 15 minutes of questions, but I want to bring useful quantum computing to the world, and uh, thank you for your time, and I appreciate the forthcoming questions.
Thanks, Nick.
Okay, I might have to reshare that. I don't know if we'll see if what the questions ask about.
You're good. I think we had some questions in the Q&A if you can view that.
Oh,
If you don't see it on your little bar, it might be under the More tab. Or
well, I
I
see
can
in the
also,
chat. Um,
yeah, there's also some in chat. But let me know if you want me to read these for you.
yeah. How about that? I usually
Let's
can't
do that.
both at the same time.
Yeah, there's a lot of just stuff going on when you're presenting.
Right.
Okay, so the first question is, as we know, the power for using quantum computer for solving the problems. So in the hybrid algorithm, why we need to combine between them. Okay. So why do we need to combine hybrid algorithms when we believe that quantum computers are so powerful? What's the
Right.
benefit of them?
Okay. So one of the things that in this particular case, this molecule, there is feasibly a quantum algorithm that would allow you to calculate those energies exactly. That is true. But practically, that Hamiltonian, so in the quantum physics language, the Hamiltonian is the operator that corresponds to the observable of energy. So the Hamiltonian is what you give the quantum computer and it spits an energy out, and you want to minimize this energy. For even the reasonable molecule that I showed, which is like just 8 atoms, you have millions and millions of terms in that, and each one of those terms with these kinds of or the algorithm we know right now would not work because it would be just such a deep circuit. Although we could feasibly run it, we can't implement it. And so the ones that we can implement rely on making measurements of each of those individual terms, but there's just too many of them. So the amount of measurements you would have to take, I think for that was estimated to be like um, 10 million years or something like that, even if measuring them like faster than we can measure right now. So that means that so the current algorithmic work is basically it's going to be a cost between the error from having depth, the depth of the circuit, and the inability of classical computers to be able to do it. So this is kind of a hybrid algorithm in that right now the quantum computers are too noisy to do the exact solution we know. So we do a hybrid algorithm where we try and get the best information out of the quantum computer. But those techniques would require too many measurements to do it exactly, kind of. So we take the information out of the quantum computer, we reduce it to a small enough problem for a classical computer to handle. And that's basically how that works. So in some way is like once I take that probability distribution and I chop off like the small bits of it, then that problem becomes is small enough for me to throw at a classical computer, and that classical computer can run over and over and over again, and there's no noise, there's no limit to how long I can run that. So that's the hour and a half that you have of classical computing time. But each one of these quantum algorithms is currently running on the order of something like 100 microseconds. To put it in perspective. So each one of those shots, the quantum operation parts is about, 100 nanoseconds, 100 microseconds or so. Each of the pulses, though, is like 100 nanoseconds or less. So you can do a lot of them.
Yeah, I was quite surprised by that runtime.
Yeah. I
An
mean,
example.
these things really add up. And so the exact simulation of these things, like if you had a very, very low error quantum computer, then you could do all of that in the time evolution. You could do that all in the algorithm instead of on the measurement side, and then you'd be able to do it roughly. But a lot of the algorithms are a give and take. Like I can run shorter circuits, but I have to do more measurements. You no such thing as a free lunch. You're going to pay for it somewhere. But we can, you can engineer where you pay for that. But that's, the reason why this is the way it's executed is because we can't do the long ones, so we do the short ones, and so then we need to do more measurements and hand it off to a classical computer, practically speaking.
Let's see. Next, we have how can a QRNG designed in Qiskit be integrated with a quantum key distribution protocol?
So if you're generating a quantum random number, I mean, you can do a coin flip. I know there's work that people have made for, bias-free random number generators. Well, your random numbers that you can get out of that can then inform the basis that you're choosing for your quantum key distribution. So that's one way off the top of my head.
Okay, one general question from my side. Can you mention some research area in quantum computing in the next 5 to 7 years that will grow rapidly with the industry and academics? Thank you, I said.
Ah, yes. Um, okay, so like, I talk to a lot of people like theoretical chemists or computational chemists in universities and computational material scientists in universities. And what you've seen like over the past, say, 20 years or so, I think, is people started using GPUs, these graphics processing units that are very popular with AI. They were first used for graphics, for doing like these matrix multiplications for generating and rendering animations, for example, video games. And then some professors, like some chemists, I think it was chemistry professors or their students figured out that I can actually do a lot of these approximations much, much, much quicker with these GPUs. And so they started using the GPUs to do these approximate methods, which give you a better approximation than any other classical method. So this is all classical, but this is like people were moving from doing CPU problems to doing like GPU problems. And now with the quantum processing units, a lot of people are saying, well, now I expect the quantum processing unit to exceed that what I can do with GPUs because I can do it. I could do it to a better approximation. I can do it more accurately with the quantum computer. So I think in what I talk to a lot of people, just modeling nature is something that a lot of chemists and physicists are doing in the universities. Um, but I also find that a number of people in the engineering departments are very interested in using and even thinking about the interplay of how do you arrange these three different kinds of computing. So that's one of the things we talk about a lot at IBM is the there's a lot of different ways of computing and how do you efficiently put them together in a lot of ways. So that's kind of a systems engineering level that a lot of electrical engineering professors would be into, for example. But there's also like things like compiling, there's things like quantum error correction. There's a lot of theoretical aspects that go into quantum computing or doing quantum computing better that I think can excite all kinds of researchers.
Great, thank you. Okay, let's see. Um, okay, here's a good question that I've asked myself when I got into this. Can we execute quantum algorithms on classical computers, i.e., using a virtual system, or do we need to build a quantum computer to do that?
Okay, that's a great question. I mean, that's something people talk about all the time. So if you want to simulate what a quantum computer can do, basically, like on the earlier slides, all of these quantum operations are just matrix math. And the problem, well, if the matrices are small enough, you can put them on your classical computer and you can calculate things. Um, this kind of matrix math is also what GPUs are quite good at because you can do a lot of it in parallel. What happens though is every time you add a qubit, you double the size of the matrix you need to store. So that column vector, when you add a qubit, it becomes twice as long for each qubit you add. So what happens is you get to the area of like 50-ish to 100 qubits, you can no longer represent that matrix on a classical computer. The problem has gotten too big for the classical computer to handle, but not for the quantum computer to handle. And so that's why for small scale systems, you can use simulators that can do exact simulation. There's also a lot of ways of adding noise to the simulation to make it more realistic. That's also something that people do a lot. And there's a lot of, a quantum mechanical field called open quantum systems that deals with a lot of that, but also informs a lot of what people do for quantum error correction. Because if you can model and understand the noise, then you can do a better job of getting rid of it. But yeah, so that's basically what breaks down. Tensor network methods can also represent a large degree of entanglement. Um, but a lot at some point it becomes approximate, so that breaks down as well. So there's tips and tricks that people have gotten, but fundamentally these matrices just get too big to represent with anything classical.
Great, yeah, that's a great explanation. I'm just checking the chat real quick to see if
Yeah, yeah,
there's
absolutely.
any thing that I missed. Mm, Okay, hold on. Here's a question. How can we determine whether a certain problem can be solved more efficiently using a quantum computer rather than a classical one? I think this is the grand question the whole
Yeah,
time.
I mean, that's something a lot of people want to know. So a lot of like the exponentially powerful quantum algorithms that are known rely on a subroutine called phase estimation. Phase estimation is basically something that allows you to find the eigenvalues of a matrix. So it allows you to represent like a much more complex matrix in a much smaller way, and is a very it's a tough matrix math problem, and it has a lot to do with measuring observables um, and the like. So if you can somehow, map your problem into an eigenvalue problem, then I can probably show you how a quantum computer would have a exponential advantage. Um, but there's a lot of things that we think, there's a lot of things that don't use that we think have a potential as well. Maybe you don't get an exponential advantage. Maybe you get a polynomial speed up, for example. So maybe you want to use a quantum computer for that. Um, Sometimes people just especially in the, I'd say, machine learning field, people just put quantum parts in, and if they get a better answer than they did without the quantum parts, then that's better. And that's how people treat machine learning because they just want to get a more, a more accurate answer, for example. Um, some of the newer stuff, like I think in optimization and differential equations, for example, this is all pretty new stuff that people are thinking you can solve with quantum computers. And a lot of it is we don't really know until you try it, until you have a problem, you try to figure out how to map it to a quantum computer. And that's why we need to, educate all the students and help researchers in the universities and stuff like that, because we need people to discover more algorithms so our quantum computers are more useful. Um, so yeah, but that's a great question. I mean, I think there's no known answer for that right now.
Yes. If you know, then we want to hear from you.
Yeah,
So,
right. There's a lot of unknowns in this field, and there's a lot of what's fun about quantum computing is involves a lot of subdisciplines, like very that can be very different from each other. And you always hit a wall of knowledge somewhere where you just don't know the answer anymore, and you basically just got to go try it out.
let's just do a couple more questions. I like this one that came in. In classical computing, the software stack allows us to develop application with a high level of abstraction, and we do not need to manipulate bits. Is this also the future of Qiskit, or due to the nature of quantum, do we need to develop it at a low level of abstraction and manipulate qubits to develop
Yeah,
applications?
that's a great question because you definitely, we look to the history of classical computing for a lot of the inspiration for like how to make this work. And clearly, classical computing had a lot of technical challenges that were overcome, and we kind of see how that worked. Um, what I would usually say right now is if you try to make things modular too fast and try to abstract away too fast, what you'll usually have is just a worse algorithm. And so when I talk to um, like my friends who have more computer sciencey background, a lot of times I would say, before people used to hand optimize machine code and they didn't trust the C compiler to give a better answer. Um, and I'd say that's probably true right now, but eventually the C compiler gave a better answer than hand machine compiled code, but we're not at that level, and that has to do with like all the errors we deal with in quantum computers because you have to be a lot more careful about how you map the problems. That if there are ways to abstract it and do it digitally, it's just you won't get a great answer. And so if you don't get a great answer there, you'll get too many errors. You won't get a good answer out of the quantum computer. So that's kind of how I think about it. Yeah, we definitely want to go in that direction, but right now we can't.
Yeah. I think some of us who are researching quantum computing also just enjoy that low level aspect of seeing the cool quantum mechanics tricks that we're playing behind the scenes.
Oh yeah, yeah. There's a lot of tricks out there.
Yeah. Also, I just want to say hello to the 76 participants joining us online, and we also have a good group of people here. If you joined late, we're just wrapping up this Q&A with Nick. Let's take like two more questions and let's see, let's pick them now. Mm. This one's a a short one, but I think it's very a common misconception or question that people have. Aren't quantum computers always faster than the classical ones?
Quantum computers get their power from calculating things differently than classical computers. And um, if you just look at like the clock rate of like a classical computer, your laptop probably is like 5 gigahertz or so. So that's 5,000 computations a second, roughly. Um, this is cycle speed. The rate at each calculation can be done. There's like what's that, 5 gigawatts, not 5 billion per second. So that's a lot. We are running our quantum computers a few thousand times a second. So that's like kilohertz versus gigahertz. So it's like 4,000 versus 9 billion is just the clock rate. So if you had a problem that doesn't get an advantage from running on a quantum computer, it would A, be slower if you ran it on a quantum computer. B, it would be more error prone to run on a quantum computer. So if you have like classical types of problems, then just run it on a classical computer. You have basically no error. I mean, the error rate for our qubits like is 1 in 10 to the 3, and for a classical computer, it's like 1 in 10 to the 27. So 23 orders of magnitude will show you that if you can run it on a classical computer, well, you probably want to do that. Now, we're getting to the point where a lot of us say like big sources of energy consumption. are causing people to think that you could actually maybe run things more energy efficiently on a quantum computer. So that's just a different kind of metric if you don't care about how fast it is, or maybe it is conducive to quantum computers. But usually, if you want a good answer, I would run it on a classical computer unless it was a problem that you think there would be you have a reason to think there's a speed up for a quantum computer doing it. Yeah. I mean, theoretically, you can run anything on a quantum computer, but you just don't want to do it that way. Just
Yeah. And I don't think quantum computers will replace our personal
yeah,
portable laptops anytime soon.
we're
So
very clear that
wherever,
all different kinds of computing have a purpose, and we never see quantum computers replacing classical computers.
yeah.
Well, kind of for that reason. I mean, Moore's law's done a great job, even if it's come to an end. We still have 5 GHz speed chips.
Let's see. Okay, maybe for this last question, you can kind of plug IBM Quantum on the Cloud. Uh, how
Yeah.
much computing power does IBM provide the community to solve quantum computing problems?
Oh, it's a great question. So for the community, any member gets 10 minutes for free a month, and 10 minutes, you can do the math, but you're running circuits at about, a few thousand a second. So each second of that access gives you like 4,000 experiments. So you can get quite a bit of usage out of it. A lot of it also depends on the algorithm. Variational algorithms are very expensive in terms of quantum resources, so it's not much in terms of that. But even for this, the results I showed with the 77 qubits and the iron sulfur catalyst, that took like 45 minutes. And that was done, by us, using a multiple of the access we provide for free. So you can get some pretty good stuff out of the free access, but it's going to limit some algorithms, for example.
Okay, I'll give a last call in the chat, or maybe we can just start sending our thanks to Nick for giving us a great starter presentation. Um, but yeah, thank you so much for answering these questions.
Absolutely.
He was gracious enough to provide his LinkedIn for us. So if you all want to keep track of his work and see what he stays up to in the next coming years, please connect. And for today's lecture, we'll share all of these slides and the recordings once the event concludes. So we get to rewatch this and have it as a reference. So thank you so much again. Um,
Absolutely. It's a pleasure to be here. Thanks for all your delightful questions.
yeah. So
And
before we get to my super fun lecture, let's take a 5 minute break and join back at um like 3:15. How's that sound? And thanks, Nick. You're welcome to stay and join, but otherwise, I know you have a busy day, so we appreciate you coming.
yeah, I'd love to, but I probably need to go do some stuff.
It is a Monday, so
But it was a pleasure being here. I'll see you around the community, Natalie, and thanks all for attending, and hope you enjoyed it.
yeah, maybe we'll come back next year for our, revamped Qiskit Fall Fest. So
Absolutely.
okay.
All
See
right.
ya.
Take care.
Thank you.
Bye.
Okay, guys, let's take 5 minute break. I'll get my slides all loaded up and then we'll talk about a quantum algorithm together. Okay, hi everyone. Welcome back. Um, you guys gave great participation and sent in a bunch of questions. Sorry I didn't get to all of them. I'll have my co-organizer, Dr. Sierra Sosa. He'll be in the chat answering questions. Um, so look out for that. But thank you so much for your support with our speaker. Let's see, let's get on to my presentation for the day. Okay, so today I kind of wanted to follow up Nick's lecture. First, I just want to say another thank you for him. And, it means a lot that we get someone from IBM to go ahead and start out this series with us. I wanted to build upon his lecture by giving you guys and walking you through an overview of a algorithm that um, has cemented itself in quantum computing history, and that is the Deutsch and Deutsch-Jozsa algorithms. Um, I also kind of want to talk about what is a quantum algorithm, and then lastly, I'm going to share all of these uh, topics. I'm going to share the IBM quantum learning module that's associated with them because I purposely chose problems that you guys can go and explore at home if it really piques your interest. Okay, so um, in the future, um, we know, or okay, so in the future, we hope that there are certain problems that we can simulate on a quantum computer that are going to show um, a massive speed up when compared to quantum algorithms. And right now, we're at that phase that we discussed with Nick, where we're trying to figure out what are the problems that are best suited for a quantum computer, and what are the ones that should just stay in the classical realm and are perfectly fit to just be classical algorithms. And that is kind of the research question that people in quantum algorithms fields are working on right now. And it's something that makes the field super interesting to get into because there's just so much opportunity for questioning and developing in this area. So to start off, if we want to talk about quantum algorithms, we should explain kind of what a classical algorithm is. And all of you with our CS background have heard the anecdote before that a classical algorithm is kind of like a recipe where it's a step-by-step procedure that we follow to solve a problem. And these classical algorithms are performed on classical computers. As computer scientists and people who write classical algorithms, we often don't really focus on the relationship between the algorithms we're writing and the computer hardware that we're running on. Because as um, kind of like a property of our classical algorithms, we try to abstract them away from the hardware itself so that the basic instruction set that describes our algorithm can really be implemented on any classical hardware. Okay, but when we introduce a completely new form of hardware in the form of quantum computing, we can no longer translate those basic instruction sets onto quantum computers, and that gives way for quantum algorithms because what we need now is step-by-step procedures that are written in this quantum instruction set that are being that are built to be ran on quantum computers. And this means that we need to focus on algorithms that are going to utilize the natural features of a quantum system in order to solve problems, including superposition, entanglement, and interference. So because we have such a new tool set to use, we're able to create these new algorithms that the goal would be to find algorithms that show efficiency over their classical counterparts just by using these quantum features. When we talk about quantum algorithms, it's good to get kind of a basic idea of the structure so that when you see a new algorithm, you kind of know what you're looking at. If the goal of our quantum algorithm is to take a quantum state and then transform it into an output quantum state, then we first need to begin by encoding our input and initialized state. And oftentimes we're taking a classical data set or a classical input and encoding it into a quantum state. And that's the first setup. And this quantum state typically is using the properties of superposition in order to kind of take advantage of that exponential state space that superposition provides for us. And then next, once we have our input states encoded into our quantum state, we're going to perform a series of operations on them in order to transform that state and obtain a quantum state that encodes the solution. Lastly, we can't forget that we have to measure our results at the end so that we can get a classical result that we can interpret and use. And we often have to really focus on this measurement step in order to obtain the most amount of quantum data that was processed throughout this algorithm and not lose any information just by through the collapse of our superpositions. Okay, today I wanted to talk about what is commonly considered the first quantum algorithm, and that's Deutsch's algorithm. It was developed by David Deutsch in 1985. And this problem really demonstrates kind of an example of a problem where a quantum computer could solve something more efficiently than a classical computer. And at this time, think of this as the first quantum algorithm. He was trying to make an example that would get people inspired to do more research into the field in order to find problems that are more useful and have more practical applications. So his algorithm, it utilizes and demonstrates a lot of those quantum features that I was talking about, specifically quantum parallelism and interference. But ultimately, this algorithm is kind of like a toy example, but I think it's the perfect place to start when you're first getting into quantum computing because Deutsch's algorithm, it operates on 2 qubits, and the example, when you are looking through the theory, it can be written out by hand. And I think that this is a great place to start if you're getting into quantum computing and you want to go beyond the surface and you want to start deeply understanding these algorithms. If you're able to work through this one, then I think you're in a great position to start focusing on more advanced algorithms. Okay, so let's talk about what the objective of Deutsch's algorithm is. So let's propose let me move my Zoom thing. Okay, our problem is that we have this black box, and within this black box, there is an unknown function to us. So in this case, the function is one that takes one input bit of either 0 or 1, and then returns to us one output bit, which is also 0 or 1. And what we want to do is, through the use of quantum properties, we want to extract some information about this unknown function so that uh, we can, compared to the classical version of this, we can prove that there is a quantum speedup for this problem. So this function, we want to know if it's constant or balanced. And when it comes to this problem setup where we only have one input qubit or one input bit and then one output, there is only 4 possible functions that could live in this mysterious box. Um, and let me move this over, sorry. Okay, so there's only 4 possible functions, and they're listed here. Just to give you a kind of explanation about what this graph is saying, right here, this x would be the value of our input bit, and then this f of x would be the output for a specific function. For f of 1, if we input a 0, then we get a 0 back. And if we input a 1, then we also get a 0 back. So this kind of function where when we give it any input, we get the same output back each time. This is called a constant function. And on the other hand, when we give the input to our function and we equally get back a 0 or 1, that's called a balanced function, which are f2 and f3. Okay. So the classical approach to this, and the way that we're going to compare this to the quantum approach about the efficiency speed up, for the classical approach, in order to determine if this function, this mysterious function, is constant or balanced, we would need to run through this step for each one of the possible input values. And each one of these steps is called a query. So for the classical approach, we would need to do 2 queries to determine if we have a balanced or constant function. And this example, it walks through the f2 function where if we give it a 0, we get a 0 back. If we give it a 1, we get a 1 back. You see, we wouldn't be able to determine just from one run of this classical example if we could get that property of being balanced or constant. So we'd have to run it twice. Deutsch's algorithm, on the other hand, only requires 1 query in order to determine this property about a function. Pictured on the screen is the entirety of Deutsch's algorithm. That's why I love it as an intro algorithm, because it's very digestible in its size, where we can kind of walk through it together about what we're even looking at in this image. So if you're super new to quantum computing, we can describe a quantum algorithm as a circuit, which is depicted here, where each one of these lines represents 1 qubit or 1 quantum bit that we're operating upon. In this example, we have 2 quantum bits. We have Q0 and Q1. And these squares are operations that we're performing on these qubits in order to manipulate their data. These are called quantum gates, and that's kind of the visual essence of how we depict quantum circuits and algorithms for quantum systems. If for this example, we are trying to achieve a measurement of 0 if the function is constant and 1 if it's balanced. And we'll continue to work with the F2 example as our mystery function. In the quantum algorithm, the mystery black box is represented by this U of F right here. You do not have to know what the function is inside of this unitary operator is while you're performing this algorithm, but it's helpful for us to know what the end result would be while we're working through it. so that you kind of get an idea of like, okay, that's why this is happening. But in this quantum circuit, we're going to encode this function, U of f, which is just this operation right here. Um, okay. Now let's just go a little deeper into the quantum circuit. Okay, so you remember how I told you we have 2 qubits for this example and for this algorithm? Um, a lot of times in quantum algorithms, we're going to give each qubit a purpose, especially as we're encoding things. For this algorithm, we have the qubit 0. The purpose of that one is it's going to keep track of our input bit value, X. Okay, and then the lower one, qubit 1, that is going to hold information about what that output value is going to be. Since we're utilizing quantum parallelism within this circuit, we are putting our input value and output values in superposition in order to kind of work through both of these options for input values at once. Let's see what else we have going on. Okay, so right now we're going to break down what we're doing at this first portion of the circuit. Okay, so in this upper qubit, qubit 0, we're putting that in a superposition by applying a Hadamard gate, and we can write that quantum state as this notation right here, where what this is pretty much saying is that we have a kind of like a probability of one half of collapsing into the 0 or the 1 state for this top one after we put it into superposition. For this Q of 1, we apply this NOT gate before we apply the Hadamard gate. And what that does when we prepare this bit like this is eventually it's going to allow us to utilize interference when doing computation with this circuit. So we can write these 2 qubits as like one composite state, because what you're looking at here within the circuit, it's representative of one composite quantum state of all of these qubits. And we can write that as psi1 right here, where hold on, I have to move all my Zoom stuff. Where in this notation, when we write these states combined, you can kind of imagine that each component of this is depicting one of those qubits, even though we're writing it as a composite system. So in this scenario, this vector right here for 1 and 0, that's going to be pointing to the 0 qubit. So stay with me. All I really want to try to say is notice the structure of this state right now, because after we apply our black box function, which we can actually describe as a controlled NOT gate, if we are trying to encode F2 as that unitary, because when that 0 bit, qubit 0 is 0, we want our output to be 0. But if our qubit 0 is 1, then we want to enact this controlled NOT gate to also transform this lower one into a 1 as well. That's why we can take that black box and replace it with a control NOT gate. Okay, so after we apply that control NOT gate, what happens to our quantum state is that we change the relative phase of our state to negative, and that impacts uh, our qubit zero when that state is one. So what happened was we are applying a controlled NOT gate to this lower qubit. And when we expect to measure and do computations when this qubit zero is at one, um, intuitively, you would think that this qubit zero would not have an impact, but this is kind of one of the um, non-intuitive quantum features that come up in these algorithms where things just work in a way that you wouldn't exactly expect. Because after we apply this control NOT gate, we're actually changing and having a change to this qubit zero. And what this ultimately does is this is happening because of a phenomenon called phase kickback, which when you're first getting into quantum computing, it's kind of non-intuitive. But one way that I had it described is that when you're canoeing, you're pushing backwards, but you're actually propelling forwards. So what you think you're doing, like pushing backwards, you think it's going to affect, what's behind you. It's actually moving you forward. It's kind of like this in our quantum state. But after we apply this Hadamard gate to our qubit zero, if our function was balanced, we're going to measure a one. Because now that we're undoing this Hadamard gate here and we have this negative relative phase, that ends up reverting back to a one state instead of a zero state. So for this example, what we're getting is a one that lets us know that our function was balanced. And this was kind of a modest speed up when compared to the classical example where we needed two queries. We only need one this time. But what this algorithm did was inspire more algorithms, including an extension of the Deutsch's algorithm called Deutsch-Jozsa, which is a multi-bit extension of Deutsch's algorithm, where we can determine whether a function of n bits is constant or balanced. And the speed up from that is taking, in the classical sense, it's 2 to the n queries that are required. Now we only need one shot still in this multi-bit example. And just pictured here, to give you an idea of what this looks like, here's an example of the Deutsch-Jozsa's algorithm for a 3-bit input function. And then it has one qubit that is helping us with that output. It's a very similar structure. The math just gets more complicated behind it when you add more bits to it. So takeaways from this algorithm. If you're someone who's new to quantum computing and you just are completely lost, like that's okay. Because the problem, or the kind of something that I came to really enjoy about quantum computing is that, these are problems that you're not going to understand intuitively on the first time, and you need to slow down and review all of the steps and how they're impacting your quantum state over time. And that requires just spending quality time working through your Dirac notation and really reviewing the circuits. And I think that this example that utilizes superposition and also interference to get us the result that we want to obtain in the end is kind of just one of these like quantum tricks that we were talking about earlier that really can be just super fun to learn about because, in a lot of classical algorithms, it's pretty straightforward, and there's nothing like that uh, can super, just you just have to stop and ask yourself, like, okay, how did that even do that? But I think that's part of the really cool, like, subtle quantum phenomenon that we can see in these quantum algorithms. And lastly, this is just a toy example, but considering the history of this at the time where we published this, and this really made people ask themselves, okay, great, there's an example. Now, are there more interesting and practical problems to be solved using quantum algorithms? Um, and it turns out that over, the past several decades, we have discovered that there are a suite of problems that quantum computers are best suited for, including quantum simulation problems where we're simulating quantum systems using a quantum computer. And that follows very naturally and intuitively of why those would benefit quantum algorithms. We also have the set of quantum algorithms based on the Fourier transform, including Shor's algorithm. And then also, thanks to Grover's principles of search algorithms, we have a set of quantum search algorithms that uh, have been shown to be like the sort of problems that can be beneficial to model on quantum computers. Okay. So now what I want to leave you all with is just some resources so that um, if this kind of ideal of going deeper into the quantum theory and breaking down an algorithm bit by bit um, is interesting to you, that you can do it yourself. I also am going to include a uh, resource for Grover's algorithm as well, which today I presented you with a not very practical algorithm, but very great foundational algorithm. If you want to look into something more practical after this to challenge you, I would suggest moving on to Grover's algorithm, which the goal is to find a specific item in an unsorted search space just faster than the classical brute force methodology. Um, this is a algorithm that has shown quadratic speedup compared to classical algorithms, and it's definitely one of our foundational algorithms. So where you can look at this stuff is IBM Quantum Learning. Uh, they have two modules from Qiskit in the classroom that describe these algorithms very well and succinctly. There's also Python notebooks that you can follow along with if you want to write code for these things and run these algorithms on real hardware. So I'll leave these with you. And